methane. Looking at the radical bromination of methane, and we're just going to go to the propagation steps. For these energy calculations, when we're trying to figure out something about this reaction, we don't need to do the initiation step. We just go directly to the propagation steps. And just like in our last reaction, we'll start out with the bromine radical. This bromine radical escaped from the cage in the initiation step, and now it's hunting for electrons in our alkane. You should be able to draw the mechanism for this. I'll just draw it one time here, but you should be able to do the same mechanism, right? Just like for chlorine, it's exactly the same. But again, I don't want to do all these mechanistic steps right now, but if we do this mechanistic step, bromine wants an electron, it's going to get one from this bond, it's going to bring hydrogen along with it, we make HBr. And the other thing is familiar now, methyl radical. The second propagation step, we bring our alkyl radical, in this case a methyl radical, down, and we use Br2, just like we were using Cl2 in the last example. I'll give you the mechanistic steps here for this, but you'll see it's exactly the same as for chlorination, right? And what this particular reaction here describes is the formation of bromomethane, and we regenerate a bromine radical. In this particular series of steps, what I want us to do now is identify what bonds break, what bonds are formed, to see if you can identify them visually. We're going to fill in energy values, no big surprise there, but see if you can visually identify which bonds are breaking, which bonds are being formed. Well, luckily for you this time, this particular bond is breaking. We can see right here with mechanistic arrows that it was, and the bond that forms is HBr, and this bond is worth 88 kcals per mole. Again, you would find this in the table, and we're just going to simply subtract the two, and this gives us a delta H of plus 16 kcals per mole. On the exam, you're not going to be using any calculators, you're not going to be of any kind, you're not going to be using any cell phones to do this type of math. You should be able to do the simple subtraction without any encumbrance, right? There's no need for a calculator for this level of math, so don't pull one out. Okay. Second reaction, BR-BR. This particular bond has a different strength than Cl-Cl. This HBr bond has a different energy value than HCl. So there's some differences appearing, and you would find them in a table if I ask you to do something with that. The new bond formed in methyl bromide is the bromine carbon bond, and this has a little slightly different energy value than a chlorine carbon bond. And again, bonds broken minus bonds formed gives us our answer for this. So our first step is plus 16. Our second step is minus 24. These values we calculate. And then if we want to calculate the delta H total for the reaction, in this case it's minus 8 kcals per mole. It's just the summation of these two numbers. This number here, and this number here, and this number here all tell us something about each step. The first step is endothermic. It's very highly uphill. The second step is exothermic. It's very negative and downhill. The overall reaction is negative and exothermic. And that means the products of this reaction are more stable than the starting reagents, and that's why this reaction works energetically. We're going to take these numbers, we're going to graph them just like we did before. The numbers that we're really looking to graph here are 16, 24, and minus 8. They come from the calculations of bonds broken minus bonds formed, bonds broken minus bonds formed. If you added all this together, you get minus 8, but these individual steps will allow us to graph this on a sheet of paper. We're going to do that right now. So this is a very, very simple exercise to do. This is energy on one axis. This is the reaction coordinate or reaction progress. On the other axis, we're always going to start at energy value of 0 or relative energy value of 0. When this reaction starts, we have methane and bromine radical. And From our energy calculation, this was plus 16. So one thing we could actually do is we could just simply go up on our paper and write plus 16, draw a line up here somewhere. This is where we're going to get after the first propagation step. We don't draw a straight line to it. There's some transition state between the 2 points, and we just draw some bend like this. Okay? This value we calculated, this we didn't, but this is a transition state. It's always going to be higher in energy than the enthalpy of reaction. In this particular case, we've already graphed here that it's 16, but we could also write right here that this is 16 kcals per mole. So we're up to here. This is the point where we've generated our methyl radical. The transition state, again, is associated with some activation energy. This value here, you can't calculate. I'm just going to give it to us today for our discussion, but it's not important. What's important is this graph in blue and red, but this particular number here, don't fixate on it, okay? For this particular reaction, it's 18 kcals per mole, and you'll recall that EA is going to have to be greater than delta H1, which in this case is 16, so this is bigger than that, and it has to be less than the bond association energy, which in this case is 104 kcals per mole. So this is where it comes from. It's a measurement. It has some outlying or bounding principles. It must fall between. It must be greater than the enthalpy of the reaction, but it's going to be less than the bond association energy. And I just want us to keep this number in mind just a little bit for our discussions about selectivity of bromine versus chlorine. But this isn't something you're going to replicate or put on an exam, okay? Just putting it here. It's an important point about transition state theory. It's a very, very powerful tool later in other chemistry classes or biochemistry classes. Let's finish off our graph here. The next thing we're going to do is we're going to go down in energy, minus 24 kcals. So we're going to go somewhere from here all the way down to minus 8 here, or minus 24 kcals per mole for our ending point. There's going to be some transition state with it. It involved a hump here. We're not going to worry too much about this particular number. I only want to talk about the first one. But going from our second propagation step to our final products was calculated being minus 24 kcals per mole from here to here. It's in our calculations, minus 24. The summation of this is minus 8. So while this is minus 24, this is plus 16, minus 24, the overall energy of the reaction at the end when we make methyl bromide plus our bromine radical is going to be down here. We can see from these two different graphs, or from the two different energy calculations, there's some differences between chlorine and bromine. The bromination reaction is less exothermic, minus 8 kcals per mole. The chlorination reaction was minus 25 kcals per mole. One of those two reactions liberates a lot more energy, is more reactive, and is less selective. Chlorination liberated much more energy, was much more exothermic, is much more reactive, and then less selective. Bromination liberated less energy, still exothermic, but it's less reactive and more selective. The relative heights of these transition states don't matter for us. This value, though, has to be higher than this one. This value here has to be higher than this. That's the only key thing. If you want to draw it off the sheet of paper, I don't really care, but it can't be a straight line down. So this is a great question, Ellie. We just don't have a line going from here to here. All we have to do is just show that there's some hump here. There's some transition state here. Don't know what it looks like. Don't need to do any calculations for it, but these are how these graphs actually work. Okay, so the points that are important that we can calculate are here, and we start from 0. We go to here just through some transition state. We go from here to minus 8 through some transition state, or we go down minus 24. So these types of graphs really aren't that difficult. And the questions you're asking are fine here. Again, can't calculate, can't know it, but it can't be a straight line from here to here. It's just not how nature works. To get to here, we have to traverse some transition state that's very reactive. To get from here to here, We also have to traverse some transition state. We don't know what it looks like exactly to get to here. Okay, so those are some key bits here. Thanks for your patience in following along. But these types of graphs you should be able to replicate with some level of fidelity.